Good morning, students. In the earlier two videos of lesson number 9, force and laws of motion, we had discussed about definition of force, the effects of external force on the body, balanced and unbalanced force, Galileo's experiments on slopes, Newton's first law of motion, practical examples of Newton's first law of motion, momentum, inertia and mass, Newton's second law of motion. We had solved three numericals. Now moving on further to the fourth numerical, example number 9.4. If you observe the textbook, the question is given a force of 5 Newton gives a mass m1, an acceleration of 10 meter per second square. Now here you can see you are given the force 5 Newton and acceleration is given 10 meter per second square. But the mass is missing, which you have to take as m1. And a mass m2 having the same force, but the acceleration is 20 meter per second square. So what acceleration would it give if both the masses are tied together? But before finding the acceleration when the body is tied together, we need to find the mass of the two bodies individually. So first of all, we'll write down in the solution, we are given F equal to 5 Newton, A1 equal to 10 meter per second square, A2 equal to 20 meter per second square. Here you require to find M1 and M2. The mass formula is M1 equal to F upon A1, that is 5 upon 10. The reduced form of it is 1 by 2. 1 by 2 is nothing but 0.50 kg. M2 is force remains constant F upon A2, that is 5 upon 20. The reduced form is 1 by 4, that is 0.25 kg. Now you are told that if the two masses are tied together, then what would be its acceleration? So if the two masses were tied together, the total mass m would be m1 plus m2, that is 0.50 plus 0.25, that is equal to 0.75 kg. Now A is the acceleration produced in the combined mass by 5 Newton force. So small a equal to capital F upon m, that is 5 upon 0.75, which can be written as 5 upon 75 upon 100. The reduced form of it is 20 upon 3, that is 6.67 meter per second square. One more time. In this question, you are given a force of 5 Newton gives a mass m1, an acceleration of 10 meter per second square, and a mass m2, an acceleration of 20 meter per second square. What acceleration would it give if both the masses were tied together? F is given 5 Newton, A1 is given 10 meter per second square, A2 20 meter per second square. M1 you require to find, M2 you require to find. M1 equal to F upon A1. Its reduced form gives us 0.50 kg. M2 equal to F upon A2, that is reduced form gives us 1 by 4, that is 0.25 kg. If the two masses were tied together, the total mass M would be M equal to M1 plus M2, that is 0.50 plus 0.25, that is equal to 0.75 kg. A is the acceleration produced in the combined mass by 5 Newton force. A is equal to capital F upon M, that is 5 upon 0.75. Its reduced form gives us 20 upon 3, that is 6.67 meter per second square. Now moving on to the next sum, example 9.5. In this velocity time graph of a ball of mass 20 gram moving along a straight line on a long table is given. If you see in the graph, this is an example of retarded motion. So here the 20 centimeter per second, which is shown on the graph, becomes a initial velocity, whereas the final velocity would be 0. So mentioning whatever is given in this question, m is given 20 gram. Initial velocity from the graph itself, we can see it is 20 centimeter per second. Its final velocity is 0 as the vehicle, you can see in the graph, is in retarded motion. In order to find acceleration, A is equal to V minus U upon T. That is 0 minus 20 upon 10. It is minus 20 upon 10, which gives you minus 2 centimeter per second square. But we need to convert it into meter per second square. So we'll divide it by 100. So the answer is minus 0.02 meter per second square. The mass is given in grams. In order to convert it into kg, we will divide it by 1000. That is 20 upon 1000 gives you 0.02 kg. The force is nothing but the product of mass into acceleration. 0.02 into negative 0.02 gives you negative 0.0004 Newton force. Here negative sign indicates that the frictional force is applied in the direction opposite to that of the motion. I repeat, in this question, from the velocity time graph, you can see that the body is performing retarded motion. So the velocity given in this graph, that is 20 centimeter per second, becomes your initial velocity, whereas your final velocity will be 0 meter per second. The mass of the ball is given 20 gram. In order to find acceleration, acceleration is V minus U upon T. That is 0 minus 20 upon 10 minus 20 upon 10, which gives you minus 2 centimeter per second square. But converting it into its MKS unit, in order to convert centimeter into meter, we divide it by 100, which gives us negative 0.02 meter per second square. The mass is given 20 gram. That is 20 upon 1000, which gives us 0.02 kg. Force is nothing but the product of mass into acceleration. So that is 0.02 into negative 0.02, which gives us negative 0.0004 Newton. A negative sign indicates that the frictional force is applied in the direction opposite to motion. The most important theory part of this chapter, that is law of conservation of momentum. The statement suggests in the absence of external force, the total momentum of a system comprising of two or more interacting bodies is constant. I repeat, in the absence of external force, the total momentum of a system comprising of two or more interacting bodies is constant. Suppose the masses of two moving balls, A and B, are m1 and m2, and its initial velocities are u1 and u2. Here, u1 is greater than u2. Force exerted by ball A on B during interaction is FAB, whereas force exerted by ball B on A would be FBA. After collision, the velocities of ball A and B would be V1, V2, V1, V2. There is no external force acting on the balls other than that of FAB and FBA. Before collision, the momentum of ball A, which is denoted as P of A, will be M1U1. Momentum of ball B will be P of B, that is M2U2. Total initial momentum, which is symbolized by Pi, will be the sum of P of A plus P of B, that is M1U1 plus M2U2. After collision, momentum of a ball A is symbolized as P of A dash, which is M1V1. Momentum of ball B, that is P of B dash, is equal to M2V2. The total final momentum is symbolized by PF, that is PA dash plus PB dash, that is M1V1 plus M2V2. Now, according to Newton's second law of motion, FAB, that is force exerted on body B by body, is PA dash minus P of A upon T, that is M1V1 minus M1U1 upon T. whereas FBA, that is force exerted on body A by body B, is equal to FPB dash minus PB upon T, that is M2V2 minus M2U2 upon T. As per Newton's third law of motion, FAB is equal to minus FBA, that is action and reaction are equal in magnitude but in opposite direction. Substituting the magnitudes, m1v1 minus m1u1 upon t is equal to minus in bracket m2v2 minus m2u2 upon t. Taking out 1 by t common on both the side, the bracket remains same. m1v1 minus m1u1 is equal to minus sign in bracket m2v2 minus m2u2. Opening the brackets, LHS side remains same, m1v1 minus m1u1, but minus into plus minus m2v2. Minus into minus becomes positive m2u2. Bringing the final velocities and initial velocities together, we get m1v1 plus m2v2 is equal to m1u1 plus m2u2. That is, final momentum is equal to initial momentum, which suggests that in the absence of external force, the momentum of the body after collision and before collision remains the same. Just recall this content again, as it is the most important theory of this chapter, that is law of conservation of momentum. First of all, its statement: in the absence of external force, total momentum of a system comprising of two or more interacting bodies is constant. Suppose masses of the two moving balls A and B are m1, m2, and initial velocities are u1 and u2. Here u1 is greater than u2. Force exerted by ball A on B during interaction is FAB, whereas force exerted by ball B on A would be FBA. After collision, the velocities of ball A and B would be V1 and V2. There is no external force acting on the balls other than that of FBA and FAB. Before collision, momentum of ball A, that is P of A, is m1u1. Momentum of ball B, P of B, is m2u2. Total initial momentum, that is Pi, is equal to Pa plus Pb, m1u1 plus m2u2. After collision, momentum of ball A is equal to Pa dash m1v1, momentum of ball B, Pb dash, that is m2v2. Total final momentum, that is Pf, is equal to Pa dash plus Pb dash, m1v1 plus m2v2. Now, according to Newton's second law of motion, FAB, that is force exerted on body B by body A, is equal to Pa dash minus P of A upon T, m1v1 minus m1u1 upon T. FBA, that is force exerted on body A by body B, is equal to P of B dash minus Pb upon T, that is m2v2 minus m2u2 upon T. As per Newton's third law of motion, action, that is FAB, is equal in magnitude to the reaction FBA but in opposite direction, which is denoted as FAB equal to minus FBA. Substituting its magnitude from the earlier content, we get m1v1 minus m1u1 upon t is equal to minus sign in bracket m2v2 minus m2u2 upon t. Taking out 1 by t common, we get in bracket m1v1 minus m1u1 is equal to minus sign m2v2 minus m2u2. Opening the brackets, LHS part remains same. M1v1 minus M1u1 is equal to minus into plus minus of M2v2 minus into minus plus of M2u2. Bringing the final velocities and initial velocities together, we get M1v1 plus M2v2 is equal to m1u1 plus m2u2. That is, final momentum Pf is equal to initial momentum Pi. In the absence of external force, the momentum of the body after collision and before collision remains the same.